All right, so it's going to look like we made a huge jump in our differential equations, and we did in reality, but it's all tied into the same ideas, the same questions, and the question was you still would like to solve differential systems. Only now, what I want to do is I want to show you how matrices can aid you in solving differential systems. And this is a time saver in a lot of regards. Just like if you recall, if you were one of my students in linear algebra, when I showed you how you could take a matrix and you could, row reduce a matrix to be able to solve a system, that was a huge time saver, right? But you're going to have to bear with me because this is not as simple as, hey, let me throw something into a matrix in RREF to get this, because we're not dealing with equations, we're dealing with differential equations. And what I want to do is I know this looks a little bit cluttered, but it saves me time from getting everything out. Therefore, I'm not writing as I do the videos. But we're gonna start with, just like, again, you're gonna have multiple techniques from chapter 4 and now from chapter 9. Okay, so but we're gonna start with first order homogeneous differential systems, right? So these are linear differential systems. And first thing to notice is this form right here is something that's going to pop up a lot. And it's, the idea is if it's homogeneous, then the f of t portion is going to be equal to 0. If it's non-homogeneous, then you will have an f of t portion. But we refer to this is referred to as the normal form of a system, right? So of a system of differential equations, and in fact n differential equations, meaning we can have a quantity of n different differential equations, but this is the form. This is what we call the normal form. Now I'm going to start. I'm going to start, and you're going to kind of see me bounce a little bit. So we're gonna talk a little bit about the idea of linear dependence, linearly independence, and again, if you have a decent command over your vocabulary from linear algebra, this will be a lot easier. In fact, you'll actually get to start to see how linear algebra, this overlap between linear algebra and differential equations. Now, what I want to do is, right now we're just going to practice a few different things, right? We're going to practice, for example, the first example is I want to show you, or we're going to show that the following vectors are linearly dependent, right? And other way, and now if you remember, just really quickly, I'll try to use some language that we used in linear algebra. So remember, there was, if you don't mind, come down with me down here to the bottom. So let's just say this is the following vector equation. Okay, now the c's are scalars and the x's are vectors. Now, if you recall, there was such a thing called a trivial solution. Meaning, if I just let my two scalars, c sub 1 and c sub 2, if I let those equal 0, then of course I have a true statement, right? And you would have 0 scaled to any vector is still 0. So of course that would work. Now, if there are other ways to get to 0, right? Maybe I could choose c sub 1 is 1 and choose c sub 2 is -2. If there are other ways to get to 0, then we would say that it is linearly dependent. If there's other ways, so if you have to write this down, feel free to. If there's other ways to get to 0, then we say that it is linearly dependent system. Now, if the only way that I can get to 0 is to choose scalars that are 0, then we would say that it's linearly independent. Okay, so I will come back to that as I as we proceed. So right now we want to show linear dependence. In other words, let's go ahead and write this. All right, let's write this as, so you would have c sub 1, some scalar attached to x sub 1, and I'll leave out the of t just so it doesn't get cluttered. And then this would be plus c sub 2, x sub 2, plus c sub 3, x sub 3, and that is going to equal 0. Okay, that's a 0 vector. So now the question is, if we want to show linear dependence, that would mean that there should be more than there should be more than just one way to get to 0, more than just the trivial solution, right? So we should have non-trivial solutions. Even if we can just find one of them, if you can just find one other solution other than just choosing zeros for C's, if you can find, then that just one additional way of getting to 0, that would show that it is linearly dependent. Now, what I'm going to do is I'm going to just kind of take note of something, all right? And in the way that, what I'm going to notice is that x sub 2, right? I can get to x sub 2 by just scaling 3 times x sub 1 by 3. Right? So if I did 3 times x sub 1, this would end up being 3 e to the t times 0 and then 3 e to the t. So you can see here that these are multiples of each other here, right? So we can you could think of them as they lie on the same line, if that would help you. But the other vector that we're given is it cannot be, it's not a scalar multiple of the first two. So now that actually is helpful, because if I have multiples here, then I could do something. Let's see if you'll agree with me here. If I had 3 x sub 1 minus, and I'm going to put a 1 in front of the x sub 2, minus 1 x sub 2 plus 0 x sub 3, you would agree with me that if by just as soon as I scale the vector x sub 1 by 3, and then I can subtract x sub 2, and this right here, this would zero out, correct? That would zero both vectors out because they're scalar multiples. And then all I would have to do is choose a 0 for a scalar for x sub 3, and then I would indeed reach 0. So I could reach 0 by choosing c sub 1 equal to 3, c sub 2 equal to -1, c sub 3 equal to 0. So there are not, we have shown linear dependence at this point, because we have shown that there is at least one other way of getting to 0 besides choosing all zeros for scalars. It's okay to have a 0 as a scalar, right? You just can't have all zeros, because then you would just have the trivial solution. Now, normally what you would do is you would let a much more formal way of doing this, and I'll just mention it, but I won't show it to you. You would let t equal 0. Okay, and so if we were to let t equal 0, we could form matrix A. So that would end up being 1, 0, 1, and then 3, 0, 3. Remember, I'm letting t equal 0, 0, 1, 0. So this would end up being matrix A. So when you have AX equals 0, if you recall, to solve for 0, what we would do is we would set this equal, we would add one more, we would basically turn it from a coefficient matrix to an augmented matrix by adding a column of zeros, and then you would RREF this guy. And what you're looking for is free variables. The idea that you have free variables would indicate that you have other ways of getting, and I'm being extremely informal, but it's I'm trying to call upon previous knowledge while also not assuming that knowledge is a prerequisite. So the idea that once you have free variables, you would have choices in what you could choose for for one of the variables, and that would allow us that would indicate that you have more than just the trivial solution. Okay, so let's do one. Now we'll do something very similar, except now we want to show linear independence. Now, in this case, if you have linear independence, again, let's go ahead and write c sub 1 x sub 1 plus c sub 2 x sub 2 plus c sub 3 x sub 3 equals 0, right? Because we're dealing with the homogeneous form right now. So just to make sure you understand right now, so going back to the normal form, we're gonna let f of t equal 0, so we can just deal with the homogeneous form of this of these differential equations. Now, if indeed it is linearly independent, right, then that would mean that the only way I can get to 0 is if I let my scalars equal 0. And this time what I'll do is I will work this the same way you could have worked the previous problem. So what I'm going to do is I'm going to let t equal 0. Now, you let t equal 0 so you can actually have values, real number values, instead of functions in your matrix. Okay, so what I'm doing now is I'm plugging in 0 for t for every single, and these are going to make up the column. So let's start with the first column. So this would be, we'd have e to the 0, so this would be 1, 0, 1. And this would be, we got 1, 1, and negative 1. And then we would have 1, now the 2 times 1, so that's 2, and then 1. So I hope that makes sense, that you could now think of this as c sub 1 times scale to the vector 1, 0, 1, plus c sub 2 scale to the vector 1, 1, negative 1, plus c sub 3 scaled to the vector 1, 2, 1. Okay, and again, you're trying to get to 0. So now the idea is you can go from these vector equations to matrices like so. So notice how the vectors end up becoming the columns of your matrix. And now you know what you're checking to see if there's other ways to get to 0. So what you would do is simply take your, this ends up being ax equals 0. So we want to take our coefficient matrix A, set it equal to 0. In other words, now it's an augmented matrix with zeros here. And this allows us to use, again, our row reduce form. So when you RREF this, and this is the part that you'll have to do on your own, what I want you to notice is what's left here is there are no free variables. And in other words, there's a pivot in all positions here, and If you have three equations, three rows, at most you can have is three pivots. And if you have three pivots, then what you have is a matrix with no free variables, and that basically tells us that, look, the only way that you can get this to equal 0 is if you were to choose all zeros as your scalars. All right, so I hope that the language wasn't too thick. I know for many of you, you might feel like, man, I've heard those words, but it's been a while. Just relax for just a second before you crack open your linear algebra textbook and start digging through all the old sections. Just let's let this unfold for a little bit, okay? And then when we conclude the video, then you can decide what you need to go back and brush up on. Okay. Now, what we're going to do at this point, what I'm going to do at this point is get my work organized, since I got my work all unorganized. But okay, so we're going to practice just form, right? So we have this normal form, this x prime of t equals at multiplied by x of t. We're still dealing with the homogeneous case. And if you don't mind, I'm going to be shuffling a little bit through my papers for just a quick second, because that's exactly what we're going to do. We're going to practice going back and forth between system form, general form, and so forth. So bear with me here. It appears that I got some things unorganized, and I need to organize them. I always wonder if I should talk while I'm out loud, so it's not just this uncomfortable amount of silence, but I think we'll be okay. Okay, now I'm good. So here's what we're going to do. We're going to practice just some things, just working with differential equations as systems and back and forth between matrices and so forth. So we're gonna start by given the following system. So we have x dx of dt is equal to x plus 2y, and then we have dy of dt is equal to 3x plus 2y. Okay, and we're going to do a couple things all at once. So I'm going to write some proposed solutions right here. So this is the proposed solution to this system of differential equations. The proposed solution is x is equal to 2e to the 4t, and that y is equal to 3e to the 4t. Okay? Now, this is pretty quickly, let's verify this. So this is our proposed solutions. And let's actually verify that these solutions work. Okay, well, how would we do this? Well, let's start with, since we're given the proposed solution, let's start by finding dx of dt, and let's find dy of dt. Let's do that first. Okay, so dx of dt, this is pretty easy. This would just be 8e to the 4t. And dy of dt would be, what we got? Well, that's 12e to the 4t. Okay, so in this case, what we can do is we can, to show that this proposed solution works, we could plug in for x, plug in for y, and plug in for dx of dt and dy of dt. And what we would end up with is 8e to the 4t is equal to 2e to the 4t plus 2 times 3e to the 4t. And then we would also have 12e to the 4t being equal to 3 times 2e to the 4t. Plus 2 times 3e to the 4t. Okay, and now all I would have to do is just simply show that the equations are true, that these are true. And then by doing so, I would have verified that the proposed solutions do in fact solve this differential system. Now, I'm with you that when would you ever be given the system and given a proposed solution is normally out of the ordinary, because normally you would be given the system and you would try to find you'd be trying to find the solution from the system. But I just want you to understand that let's assume that you're done after you're done finding a solution to the system, and now you're second guessing yourself and you want to know if what you just did is correct. You see how you can always substitute like I did and make sure that everything balances out. And this, in fact, would just be one of an infinite amount of solutions that would work. So I could have said 2e to the 4t plus well, I won't go through it, but you can imagine that there's an infinite amount of solutions. This is one of them. Okay, so let me now erase what I've just done, and we're going to just simply practice placing. I'm going to erase everything except the system, and we're going to practice going from the system to this normal form. Okay, so let me erase everything that I have here. All right, so let's erase everything except the system. And then we're going to practice just going from one form to the other form. Okay, so that was 2y. Okay. So we want to place, given the following system of differential equations, we want to place it in the following form. Okay. So the way you want to think about this, and actually I'm going to write underneath the system. I think it'll be easier for you to spot exactly how we're going to think about this. Okay, so let's start with what would x prime be? Well, the x prime, or x prime of t, okay, x prime of t, is a vector. Is the way you would think about this is going to be some vector that's a function of t. So that is the dx of dt, dy of dt. Does that make sense to you? That, since again we're trying to get to this form right here, so the x prime of t is this side that is the vector that's set up to represent the derivatives. So dx of dt, dy of dt. That's all under x prime of t. Now, normally you don't have y's. Okay, normally you would have x's, x sub 1s, x sub 2s, x sub 3s. But let's go ahead and continue. So now we would have to figure out what is the a. All right, well, in this case, the a is simply going to be the coefficients of of the variables for on the right hand side of the equation. So let's start with 1, 3. Right, so notice the x variable represents one of the columns of matrix A. And now we're just simply going to take the y variables, and that's going to end up making another column of matrix A. So 2, 2. All right, so that's A. And now it's A multiplied by x, or x of t. So in this case, we don't really have functions of t, but again, I just want you to see the setup here. So this last part, so this would be here, this would be here, this would be here. So the last part is going to be just the variables that you're dealing with, right? So x sub 1s, x sub 2s, x sub 3s. In our case, it's x, y. All right, so we were able to go from one form to the other. Let's continue. All right, and let's take a look at where we actually, in this, we've already done this one. So remember, I did both of these at one time. I've already verified that this is a solution to that. That was the first thing I did on the previous page. So let's go ahead and go to the next question. So given this system, the question still stands, can we write it in the following form? Okay, and I know that we're going to start off dealing with the homogeneous case, but right now we're just practice going back and forth between the forms. So this is going to be the non-homogeneous case because we're going to have some f of t. Ready? All right. So let's start. After you get good at this, you can, you can make this a little bit easier, but let's go ahead and start with the fact that you have r prime of t, and then you have theta prime of t. Those are going to make up your x prime of t vector. Right, so this is going to be composed of r prime of t and theta prime of t. All right, now the next part is we have to grab the variables, or I should say the coefficients that that make up, or that is attached to our variables. So let's go ahead and conclude let's go ahead and kind of highlight which ones are the variables that are a function of t or a function of r of t or theta of t, and then what are the constants. So let's you and I agree that sine of t is just a constant, and 1 is just a constant. Both of these are just constants. So they're going to end up going in the f of t portion of this problem. Whereas everything else, this is going to make its way into our matrix A and our X. So let's start with matrix A. So in this case, we would have, let's grab the coefficients. So let's start with r of t's. All right. So the very first, the coefficient of r of t is just 2. All right. That's row 1, or equation 1. Now equation 2, the r of t has a coefficient of 1. All right. Now let's go to theta of t. So notice that equation 1 has no theta of t's. So we're going to end up putting a 0 here. The second equation does have a 1 theta of t, and we're going to carry our negative sign with it, so it's negative 1. So 0 and negative 1. All right, so that is the a. Now, the x of t portion is going to be our functions of t. So in our case, we have r of t and theta of t. Now, if we stopped right here, we would be incomplete because it's going to be plus f of t. And these are going to end up being the constants. Okay? So we can think of it as they're constants in the sense that once you, I'm being again a little bit sloppy in my wording, but they're just simply a function of t itself, and not going through some additional function r, right? So that's just I'm going to use the word constant to hopefully that will make sense. So again, well, what's left over, right? What have we not used? Well, we haven't used the sine of t, and nor have we used the 1. So what we have here is the way you would interpret this system. And so in other words, what I'm boxing in right here is the answer. And it is of the form x prime of t equals a x of t plus f of t. All right. So where do we go from here? Well, I want to go backwards. So I want to now start with this normal form. Okay, we're going to do the exact opposite. And I want to, so we currently have our answer in this normal form, and I want to see if we can actually get to a system. Now, so this is a good problem because I'm using the subscripts, which can be confusing to a lot of students because you're used to having x prime, y prime, things of this nature, z prime. But we don't want to be limited to the alphabet, in other words. So here's what we're looking for. We want x sub 1 prime of t should be equal to, and then we also want x sub 2 prime of t should be equal to. So now my goal is to figure out this portion right here from this normal form. All right. So let's identify what the a is, and then let's use that to build our system, right? So in this case, let's start with just this part right here. If you take a look, so that's going to be the ax. All right. So let's go ahead and start with this part here. 2, 1, negative 1, 3, x. Now, again, how do we interpret that? They don't normally put the of t portion in there. I will, but normally they just leave that out so it doesn't clutter the problems. So I need to make sure you understand how to interpret that. Well, this is clearly matrix A, but how do you interpret x of t? Well, how many variables are you using here? Well, the clear fact that we have this, this 2 by 2 matrix, right? We have two rows, meaning we're in 2 columns. In other words, taking a look at the setup here, we have 2 rows, 2 columns. That should tell you something about how many variables we have. That should be 2 equations of 2 variables. So what are the variables? Well, the variables in this case would be x sub 1 and x sub 2, right? Those are the 2 variables. So again, we still have to go from this condensed form to being expanded, multiplied out. So all right, let's see if you agree with me here. So again, just like you do and we in a previous video, so this is a 2 by 2, this is a 2 by 1. So clearly we can multiply them, right? But what we're really going to do is we're going to keep them as an equation. We're not the result, it would be a 2 by 1. We're just not going to have it as a matrix. So let's see if you can follow me here. So it's going to be row 1 times, there's only one column, so times column 1. So this is 2 times x sub 1 plus, and I'll write the 1 out, 1 times x sub 2, right? So it's this row times this column. So, and now we'll do row 2 multiplied by this column. So that's going to be negative 1 x sub 1 plus, and that's going to be 3 times x sub 2. Okay, so what did you just do? Well, you just figured out how to interpret this portion of the normal form. That's the AX portion. So let me go ahead and take that and place it up here. Let's just separate it out a little bit. All right, but we still need to figure out how do we interpret the f of t portion. So we're going to do that right now. So for the f of t, we have e to the t, and then vector t and 1. Well, again, you are just multiplying. Okay, it's as simple as that. So let's start with the idea that you have, let's see here. So let's go ahead and multiply that out. Let me give myself a little bit of space. If you don't mind, I'm actually going to erase this part right here. So, okay. So what we're going to do is just multiply this guy out. So let's start. So multiplying, just like you would scale, right? If you had 3 scaled to 1, 2, what would that give you? Well, it'd be 3 times 1, and then it would be 3 times 2, right? That's if you were scaling. Now, we're not going to keep it in the matrix form, right? Because that's not the goal. The goal is to get it written as a system. But that is the idea. That is the idea of how you would multiply that out. And we're going to do this exact same thing here. So this would be e to the t times t, and then e to the t times 1. Now, all I'm going to do is I'm going to write that as t e to the t, and I'm going to write that as, obviously, just e to the t. So what did you just do? You just figured out how to interpret the f of t portion of this normal form. And I'm going to go ahead and write that. So that's plus t e to the t and plus e to the t. Now what you could do on your own time is you could see if you could go from here back to here. Right? You already know we've worked the problem one way. You could see if you can work it back. Okay, if you wanted to get some extra problem. Just like on the previous form, we started here and wrote it in normal form. You could, for just some practice, take the normal form, see if you can get back to this system of differential equations. Okay, so now what we want to do is we want to, well, actually, I think it's a good time to take a break because I've been building up some skills that you're going to need to be able to do, but we now actually want to start getting into how we solve differential equations. And we're going to talk a little bit about eigenvalues and eigenvectors, only now you're going to see them in this language of differential equations. So we'll go ahead and conclude here, and we'll pick back up in just a second.